Assalamu alaikum. Today we are going to talk about mechanical properties of a material. So there are there are multiple properties of any material. So we talk about tension and compression. So how we test compression and tension. Tension testing machine to apply an axial load with no bending at a very slow constant rate until it reach to the breaking point. So basically, we have two types of material. Some have some brittle material and some ductile material. Okay, we check tension for those material who are ductile and compression for those who are brittle. Okay, now here we have a tension testing machine in which we have which is known as UTM, Universal Testing Machine. It contains movable upper jaw, and there are two jaws, upper jaw, lower jaw. And in this, we will put our steel bar and we will apply tension, or we can make like these jaws moves apart. When they move, there is a steel bar. It will create a tension in it, and ultimately it will break. But we have to keep it constant rate, and we apply the load slowly. So it will be reached to the breaking point, and that is a tension strength of the material. Test consists of recording the elongation due to applied load. Okay. So this is stress, load per unit area, or force per unit area, and strain is change in length, elongation over original length. So basically, this is a stress strain curve of any body or any material. So in this one is like a stress strain diagram for steel. So you can see here conventional and true stress strain diagram for ductile material, steel, not to scale. Okay, here you can see in this one we have stress here. This is stress, and here we have a strain. When there is no load, everything is zero. When we start applying load, there is a strain occur in the body. Okay, initially it is linear, like whatever the stress is applied, strain occur. Initially it is linear until this point. This zone is known as elastic region, or you can say that this is here you can say modulus of elasticity is whatever the stress is applied, a strain will occur. Then there is slightly start changing, and then it will lead to the yield stress. Then it is yielding. Yielding is a point that there is a strain in the body with a constant load. Then we have like we have to apply more load, and then it will go to the ultimate stress. Then it's reached to the fracture. This point is known as fracture point, and this is the maximum stress it carries. This is the maximum stress point it carries. So this is called ultimate stress, and this is fracture stress. What is mean by elastic and plastic behavior? Elastic deformation is the deformation that disappear upon the removal of external force. What is mean by that? That when we apply the external load, definitely when we apply external load, it creates stress, and due to that stress, there is a strain. When we apply the load, external force, strain occur. Okay, but here they said that disappear upon the removal. When deformation means change in the body, or strain in the body. it will disappear when we remove the external load. What is mean by external load? Or you can say stress, when we apply stress. Elastic deformation is hence reversible and non-permanent. Like it is reversible, it can like bounce back or go back, and it is not permanent. But on contrary, plastic deformation is the permanent deformation or change in the shape of solid body under the action of sustained force. This occurs when a large stress is applied to on the substance. Plastic deformation is irreversible and it is permanent. There are two kind of zone: elastic zone and plastic zone. In elastic zone, there is a deformation. When we apply the load, there is a deformation. Okay. When we leave it, it will come back to its original position. But plastic deformation is a permanent deformation in which we apply the load and it's a constant stress. Then when we remove the load, even the body will not come back to its original shape, okay, and its original position. That's why it is irreversible and permanent. Stress strain behavior of a ductile and brittle material. A material is said to be ductile or brittle depending on its stress strain behavior. First, we talk about ductile material. A ductile material undergoes to large strain before its rupture. A ductile material undergoes to large strain before its rupture. Ductile material are often chosen by engineers because they are capable of absorbing shock or energy, and they give warning before failure. Mild steel is a typical example of ductile material. Other ductile materials are brass, molybdenum, zinc, and aluminum. Okay, so these are the example of ductile material. The ductility of ductile material is specified in terms of percent elongation or percent reduction in area at the time of fracture. Expression for the percentage elongation and percentage reduction in the area is represented by the following formula. So this is percentage elongation in length. So this is final length minus original length divided by original length. This is percentage reduction in of area. This is initial area minus final area divided by initial area. For mild steel, typical values of percent elongation and percent reduction in area are 38% and 60% respectively. Now we talk about brittle material. A brittle material undergoes to a little or no strain before its failure. Tensile failure of a brittle material is shown in the following figure. Like in the brittle material, there is no warning, there is no alarm. When we apply the load, it will sudden fail. Gray iron and concrete are the common example of brittle material. Brittle material are found to be weak in tension and strong in compression because when they are subjected to compression, any crack or imperfection in the material tends to close it. So this is a stress strain behavior of a ductile and brittle material. So this is stress, this is strain, this is brittle material. When we apply the stress, it will create a strain and suddenly it is failed at point B. This is the ultimate stress, or you can say this is a maximum load it can bear. So this is just at this point, it is failed. But here, when we apply the load on the ductile material, this is the elastic zone, elastic region. Then it go to the plastic, and then it go to the, this is the ultimate stress, and then there is a fracture. This is fracture. So this is the behavior of a ductile material. Hooke's law. Hooke's law states that within the proportional limit, the stress is linearly proportional to the strain. According to the Hooke's is the name of a scientist. According to it, that within the proportional limit, what is mean by proportional limit? Proportional means when we apply the stress, strain is increasing constantly. That is proportional limit. So according to him, that within the proportional limit, the stress is linearly proportional to the strain. So this is stress, this is strain, and this is modulus of elasticity. Where E is constant of proportionality, which is also called modulus of elasticity or Young modulus. So Young modulus equals to stress over strain. Okay. E is a mechanical property that indicates stiffness of a material. More is E of the material, more it will be stiff. Poisson's ratio. Poisson's ratio is referring to the above figure. If we see the above figure, the longitudinal strain and lateral strain are given as longitudinal strain. What is strain? Change in length per unit length. Okay, so this is longitudinal strain, change or deformation in the direction of longitudinal direction and divided by original length. Lateral strain is a strain in the direction of lateral direction, deformation and radius. The Poisson's ratio is expressed as V is equals to lateral strain divided by longitudinal strain. So this is a value of Poisson's ratio for different materials. The shear stress strain diagram. The shear stress strain diagram for a ductile material is shown in the following figure. Like stress strain diagram, there is a tau and y. Tau and lambda diagram also has a TPL and TU and TF as shown in the figure. So basically, that is the figure which we see before. It is for the normal stress strain. So this is for the shear stress strain. This figure is for the shear stress strain. So this all representation here, this one is for the normal stress strain. This is a shear strain. Okay. So we have T, or you can say strain in at proportional limit. This is ultimate and this is failure. Okay. So stress at proportional limit, ultimate and failure. Now, as shown in the figure, so it's the same figure, but here they represent it by G. What is G? Suppose G is a constant of proportionality, the shear modulus of elasticity. Modulus of elasticity is E, and shear modulus of elasticity is represented by G. Okay. Now, we know that stress is directly proportional to strain is equals to G. G is a constant of proportionality and it is represented by G here. Now G will be equals to stress, shear stress divided by shear strain. Okay. Three material constant E, V, G are related to the following equation. Like this is, what is this? G, modulus of shear modulus of elasticity, E, modulus of elasticity, and V, Poisson's ratio. If we have these three constants, it will be related by the following equation. Resilience. Resilience is an ability of a material to store energy, like energy stored by any material within the elastic region. So it is represented by stress times d strain, okay, or 0 to proportional limit. If we assume a linear stress strain curve, this simplified to this one. This suppose if we have linear, so we have say stress proportional limit, strain proportional limit equals to 1/2. It is equal to resilience. Toughness. Toughness is energy to break a unit volume of material, approximately by the area under the stress strain curve. So it is area under the stress strain curve. Here you can say that it's a small toughness of any material, it will be break, it is brittle material. It's a large toughness of a material, it's metals, and very small toughness, unreinforced polymers. So this is just a diagram, which is this is stress, this is strain diagram, which represent the toughness of different materials. Now start with the problem number 1. In the problem number 1, they are asking to plot here. They are asking to plot the above stress strain data and determine the modulus of elasticity. So this is a stress, this is a strain, and they are asking for modulus of elasticity. What is modulus of elasticity? Basically, modulus of elasticity is stress over strain. But by plotting the stress strain data, so here we have to make a graph. Okay, stress strain diagram. Okay, now to make a stress strain diagram, we have to have, it is already drawn, but I will tell you how to draw. Suppose this is 0. So here, if we have a stress strain, this is stress, this is strain. Here we have 0, first value, it will be 0 and 0. Then 33.2. So just make an interval here of, see, this is 33, 45, 49. So just make an interval of 10, 10, 10, 10. Or here make on the other strain interval. And then according to that, 33.2, make a value here 0.006. And then you get the graph, something like that. See, here they make the interval of 10, 20, 30, 40, 50, 60. And they said that 6 into 10 power 4, this is 6 into 10 raised to the power minus 4. Okay. So they make it everybody like this. So this is 6, 10, 14, 18, and 22. They have made like this. Okay. At 6, the value is 33.2. This one, the first point. Then at 10, the value is 45.5, somewhere here. Then it increased to 49.5, then 51.5, and then 53.4. So here they have the curve. Why we have to, what we have to determine? We have to determine the modulus of elasticity. So here we see that the graph is linearly increasing here. It is linearly increasing up to this point. After this point, it start making a curve. So when we have the curve, the proportional limit finish. So this is the zone where we have the proportional limit or linear behavior. So that point is the point where we have maximum stress or linear stress, and this is the point we have strain. So divide that stress into strain, you got the modulus of elasticity. The unit of modulus of elasticity is same as stress because strain has no unit, or it is inch over inch, so it will be 0. So it is KSI is a unit, so it will be KSI or K per inch square is a unit of modulus of elasticity. So now we will start with the problem number 2. In the problem number 2, you can see that we have given load and elongation for any material. So read the description. The above load elongation data were obtained for a specimen with initial length or original length of 50 mm and diameter is 12.5 mm. Plot the stress strain data and determine the E stress ultimate and stress failure. So we have to determine ultimate stress, failure stress, and E from the following data provided. So to solve that, we have to determine few things. Let me show you 1 minute. So for any stress strain curve, suppose to determine stress. Stress is load per unit area, and strain is elongation over L. Okay. Now, what is given? In our case, F is given, and due to that force, change in length is given. Okay. And original length is given, and diameter is given. So these are the things which is given. So from this diameter, we can calculate the area. Area is pi by 4 d square. We can calculate the area by using this diameter, which is I think 12.5. We will see. L naught is our original length or initial length, which is 50 mm. Okay. F and delta, F and elongation is given. F is a load. So when we determine area, then we put it in the formula. Force, F is given. So F divided by whatever the F, suppose if we have a power force 10, so, and we calculate the area. So we can get the stress from here in Newton per millimeter square. So we have to multiply by it 1000 because it is given in kilonewton. Okay. So it will be Newton per millimeter square or megapascal. For strain, it is in millimeter. That is 0.0175, I think. Whatever, we will check it. And 50. I'm just telling you the method how to calculate it. So divide by 50, which is initial length. Okay. So we will get millimeter per millimeter, that is strain. This is the way how we calculate it. Once we calculate stress, once we calculate the strain, we can determine. And what is our required? Is it required? The requireds are, we have to calculate E, we have to calculate stress ultimate and stress failure. So this is our required thing, and this is our given data. So on the basis of these data, we can interpolate and we can calculate stress, strain, we can calculate area, and then we will proceed accordingly. Okay, now go to the PDF Word file again. Here. Now here you can see that in this one we have L naught is 50, D naught is 12.5, and this is the force and this is the elongation. It is in kilonewton, it is in millimeter. Okay, 11.1 is the first, 0 is the first reading, then 11.1, 31.9, and so on. And on the basis of these load application, this is the change in length occur, 50 plus this change. So this is a change in length occur. Okay. Now, on the basis of load and elongation, we can determine stress and strain. Stress is simple, as I told you, load per unit area. This is 11.1 divided by area. How to calculate the area? To calculate area, we have diameter 12.5 millimeter. So we will put in the pi by 4 d square formula. We get the area in millimeter square. So this is in kilonewton. This is in millimeter square. So suppose if you write it like this, 11.1 multiplied by 1000, it will be in Newton divided by 122.718 millimeter square. So answer will be 90.45 millimeter Newton per millimeter square. This is first stress. In this way, you can calculate all the values of the stress. Okay. Then how many values we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Now, to determine the elongation, to determine the strain, we have to know the elongation as well as original length. So this is our original length. So we can determine it by the formula this. So 0.0175 divided by 50. Its unit is millimeter. Their unit is millimeter as well. So our strain will be 0.0003035 and so on. Okay. Now we have to plot stress strain curve. What are the things we required? We have to know. We have to calculate E. Okay. First thing, and then we have to do the ultimate strength, stress, and failure stress. Okay, so our first target is E. Okay, now draw or plot the stress strain curve. In this stress strain curve, let me copy and paste this value, so it will be easy. So it will be easy for us to see, put it here. I just copy and paste the values here. Okay, now at 0, stress strain is 0. So this is our first point. Now we make two graphs. From the first graph, we determine the E. And from the second graph, we determine ultimate failure and ultimate strength. Okay. So for the first graph, for the below one, this is, you can say, the upper graph, or you can say the below graph. Okay. Just say that. I don't need to write it. Okay. Now we have two axes. On x-axis, we have two axes. This is number 1 for the below graph, and this is number 2 for the upper graph. So we take the interval of, see, our value is 0.00035. So we just take the value is 0.01, and interval of 0.01 we take. So 0.02, 0.003, 0.004, 0.005. Okay. Now for the first one, this one, 0.0003. It will be lie 0.003 below this line. So what is the value? 90.45. So the interval here is 50. See, 0, 50, 100, 150, 200, 250, 300, 350, 40, 400, 450, 500, 550. The interval is here 50. Interval here is the below line 0.001. Okay, then plus 0.001, it will be 0.002. So this is the interval. Now 0.00035 is less than 0.0. So ideally it is lies somewhere here. Okay. So from here, the value of the first point is 90.45. So we will mark it here. Then at 0.0012, our value is 259.95. So 0.0012, it will be slightly here. So we make a second point, that is 259. So this is 0.0012, this point. Okay. Don't consider this one. Now 0.00204. So it is somewhere here. So we make a point which is 308. 308. So you can check here 308. 300 is here. 308. It's very near. Huh? So okay. So this is our third point. Then 333.28, 333 somewhere here, and it will be, the strain will be 0.033. Okay, this one. So this is our fourth point, and then we have our fifth point. Then we make a curve. When we make a curve, we can join these points with a straight line. Then here we have to experience a curve. By hand, when you draw it by hand, maybe you will make it straight from here to here, then make a curve. But when we make it on a Excel sheet, it will be shown the graph from here, like the curve from here. But it's okay. You will make it and make the graph. Once you get the graph, we have, what is our first target? Our first target to determine E. So what is E? E is a stress over strain within the proportional limit. So here you can check that proportional limit is up to that point. Then it is start curving. So we say that this is a point where we have the proportional limit. Now at this point we have to determine stress and strain to determine the value of E. Okay. Now we will drop the dotted line here. So it is 228 0.75 they calculated. We can calculate, if you calculate by hand, it is 229 or 228.75 plus minus, it's okay. And then you drop the axis here as well. So it is this line. So they consider it 0.001. Now they put it in the formula 228 divided by 1 raised to the power minus 3. You will get the E, which is 228 gigapascal, or 228 into 10 raised to the power 3 megapascal. Okay. Now we have to calculate ultimate failure and ultimate stress, or ultimate failure stress. Okay, let me clear this one. Okay, now we will make it for the second one. For the second one, the value start from 0 and the interval is like this. Here, for the upper graph, we make it 0, then take an interval of 0.05, 0.05, then 0.10, 0.15. So the interval is 0.05. Okay. And we have go up to 0.25 because our last number is 0.23. So we go up to 0.25. Okay. This is the interval we took. Now at point 1, 0. Considering this line, above line, our value is 90.45. So this is our first point. Then our value is 259.45, which is 0.001. So at compared to 0.05, it is very less. So it will be here. Then third point, fourth and fifth. They are very near. 1, 2, 3, 4, 5, 6, up to 6. Okay. Then seventh point, 435.14. So this is 435.14. And what is the value? 0.02. So 0.05 means it is 0, 0.01, 0.02, 0.03, 0.04, and 0.05. So 0.02 is here, and they make a 0.0 at point 0.02, they make 435. Then 507. What is the number? 0.06. So 0.06 means 0.05, 0.06, 0.07, 0.08, 0.09, 0.10, or 0.10. Okay. So this is 0.06. Okay. So 0.06, what is the value? 507. So we just go from here, and this is the point from the strain point of view, and 507 somewhere here. So we make a point. Then 525, 550, this is 525 in the center. We just make a point. And what is the value of strain? Strain is 0.12. So 0.12 will be 0.11, 0.12. So it will be here. Then 0.17. 17 will be after 15, 16, 16, 17. So it will be, what is the value? 507. So 507 will become again down. And then we have the last value, 479.15 at 0.23. So 0.20, 0.21, 22, 23, 24. So this is 23, and they make a value here. So in this way, we have a graph on the another side. Now, if you remember the stress strain curve, this is the point of ultimate failure. This is the point of ultimate failure where you can say that we can say that it is a stress at failure point. So this is our required result. So we have to say that 479 is the ultimate failure. They said that. Okay. In your calculation, it may be 480, 481, 478. It's okay. Don't worry about it. But it should be logical, huh? You cannot write 586 or something. It should be logical. And this is the point of ultimate stress. Stress ultimate. This is the highest point achieved by the material when it is applying the load. So this is the ultimate. So it is nearly equal to 525. This is a point we know. So this is, oh, actually this is 579. We calculated as well. Okay. Now ultimate is 525 megapascal. So our three things are required: E, ultimate stress, failure stress. So this is failure stress, 479.15. At this point, it is rupture, and this is our ultimate point where the maximum value of stress occurs. Clear? Start with problem number 3. In the problem number 3, they didn't provide you any load, any elongation. They just provide you the stress strain curve, in which we have two options. One, the upper limit, and number 1 is the upper one. Number 2 is the lower one. In the lower one, we can determine the E, if you remember, and for the upper one, we can determine the different values of ultimate failure or ultimate stress or failure stress. Just read the data first. The above stress strain data were obtained for a specimen with L0 is 2, D0 is 0.5 inch, and determine E, Py, and Pu. Now, see, the modulus of elasticity of this is what is modulus of elasticity? Stress over strain over the proportional limit. Okay, we can see here clearly this is a proportional limit. Then it is changed into a curve. So we will drop the value here and here, and we can determine stress and strain, and then calculate the modulus of elasticity. So from the above graph, we say that stress of proportional limit or strain of proportional limit equals to 40 and 0.01001. This one, down one. 0. Here you can see clearly. Here it's 0.001. So we just put the value and we get the E, modulus of elasticity, which is 40,000 KSI. Now we have to calculate Py and Pu. So what is representation of P? It's a load of force acting on an object. Okay. Now in this curve, you can see that this is a point where we have the ultimate stress, and this is a point of failure. Okay. This is the ultimate and this is a point of failure. Now we know that stress equals to load per unit area. So when we multiply by stress into area, it will give you the load. Yes. So area is unknown, and we have a diameter known. So here diameter is 0.5 inch. So we can calculate the area. Here area is pi by 4 d square. Okay. So we can multiply by pi by 4 d square into stress. We can get P. Yes. A pi by 4 d square stress. We can get P. So here we have, see, here we have Py, and here we have ultimate Pu. Okay. Now what we have to do? We have to take the value, because area is constant, pi by 4 d square, pi by 4.5 square. We have to take the value from the graph for this Pu and Py. For Pu, it's the ultimate stress, which is, this is ultimate stress. So we have dropped the bar here, and it will be approximately 77. So 77 KSI, because it is in KSI. 77 KSI is a unit for stress. So load will be in kip. Why? Because KSI means kip per inch square, and this area is in inch square. So this is only kips will be left. So it is a load. So pi by 4 d square into 77, it will be 15.11 kips. This is the ultimate load carried by the member. Now we have to calculate the load specimen with due to the yielding Py. Py is multiplied by area into yielding stress, which is we calculated here 40. So we multiply it by this. We have the same formula for this, and we have the same conversion. This is kips. For the unit, we have the same conversion. It is kips because it's inch square. We will cut from the inch square. So the answer is 7.854 kilopounds. So our three things are required. First, E, modulus of elasticity. We calculated by using the modulus of elasticity equation, stress over strain, in which we have determined the proportional limit stress divided by proportional strain. Here we can make that data here as well, that what are the things required and what are the things given. So here proportional strain is given, proportional stress and yield stress is given, which is not given. Actually, we determined by the graph. It's not given directly, but we determined by the graph. Then we have our ultimate stress, which is here. We determined by the graph as well, 77 KSI. Then put all the values in the different formulas, and we get 1, 2, 3, which are our required results. Problem number 4. The aluminum block has a rectangular cross section, and it is subjected to axial compressive force of 40 kilonewton. There is an aluminum block which is experiencing 40 kilonewton compression force. If the 37.5 millimeter side change to its length to 37.503. This is 37.5 side, this one. This side is 37.5. So this is the aluminum block. This side is 37.5. If the change will be 37.503, there is a slight strain. Determine Poisson's ratio and new length of 50 millimeter side. Where is 50 millimeter? Oh, this one. Determine the Poisson's ratio and length of 50 millimeter side. Length of 50 millimeter side. We have E for aluminum is 70 gigapascal. This is given. The sides are given. The load are given. The load is given. Initial length and final length is given. The required is this something. Okay. So this is the thing we required. Now what we have to do. So first of all, we have to calculate the stress, because we have to calculate the Poisson's ratio. As per given data, we have load, which is in compression, 40 kilonewton. The load is given, P is given. P is 40 kilonewton. Okay. And area, we can calculate perpendicular area. The load is applied on the perpendicular area, which is, the area is 37.5 length into breadth, which is 50. So we just put it in the formula. Stress is load per unit area. Load per unit area is a stress. So we have 40. Sorry, we have 40 into 10 raised to the power 3. Just make it in Newton. And because it is in millimeter square, the answer will be in megapascal. So Newton per millimeter square is a megapascal. Okay. Now 40 into 10 to the power 3, or you can say 1000, multiply with 1000 to convert into Newton, divided by 50, 37.5, which is A, area, length, and breadth. Okay. Now the answer is 21.33, which is negative, which is representing the negative sign represent it is in compression. If it is positive, it is in tension. Always remember. Now we have to determine longitudinal strain. Longitudinal strain is equals to stress over E. You can, this formula is derived from E is equals to stress over strain. So just flip this to this one. So it will be strain is equals to stress over E. So we have stress 21.3 and we know the strain as well. Oh, so we know the E as well. It is given for ammonia. It is given 70 gigapascal. How much is given? 70 gigapascal. So we put the values, okay, and we to make it megapascal, we multiply by 10 to the power 3. Okay, now we got the longitudinal strain. This is the value of longitudinal strain. Now we have to determine lateral strain. Lateral strain is in this direction. Lateral strain in the direction, in the smaller direction or in the direction of radius. But this is not a circular body; it's a rectangular body. So we have to put the strain formula. So 37.5. It is initial length, and 37.50 is the final length. It is given here. Here it is given. Here, this is given here. So our formula will be initial length or final length minus initial length divided by initial length. It will give you the lateral strain. Okay, here you put the formula and we got the lateral strain. Now Poisson's ratio is lateral strain over longitudinal strains. Lateral strain over longitudinal strain is a Poisson's ratio, which is V. So we can determine the Poisson's ratio by this formula. This is our first target. See, determine Poisson's ratio and new length in 15 millimeter side. Okay. So first task has been done. We have to go for the second task now. For the second task, it's very simple. We have to determine the increase in length in the direction of 50 millimeter side. Okay. Now we have to know the initial length plus the final length to we have to know the initial length plus strain. Okay, so we just multiply by lateral strain by the original length. We got it as 0.0004. Then we add in the 50. We get answer 50.04. Okay, if you don't understand, let me tell you in this way. See, this is what is strain? Strain in change in length, over original length. Okay, or you can say change in length over original length. So to determine change in length, we can multiply by strain into original length. So we can determine change in length. So this is actually change in length with original length multiply by strain. Okay. So because we are talking about a 50 millimeter side, that's why we take it lateral. Okay. That's why we take the lateral strain, because we are talking about the side of lateral side. So we just multiply by lateral strain by the original length, we get the change in length. So change in length plus original length is a total change in length. So this is the new length of 50, which is our required, required thing. New length of the 50 millimeter side. So the new length of the 50 millimeter side is 50.0044 mm. So this is the end of lecture number 6. See you in the next lecture. Assalamu alaikum.